Welcome students. Myself Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. I am dealing with fifth paper of MSc Final Physics, that is Solid State Physics. In my previous lectures, I have completed 2 units which cover superconductivity. We have started ferromagnetism. In my previous lectures, I have given brief introduction about ferromagnetism, and we were dealing with the Wies theory of ferromagnetism. So, first of all, I am going to give a brief review of what I deal with my previous lecture. As we have studied that this Wies theory of ferromagnetism is based on two hypotheses. First hypothesis is that a ferromagnetic specimen, it consists of small regions which we call domain, and these domains, they are spontaneously magnetized. And when we have to find the magnetic moment of our material, we have to find the magnetic moment of individual domain, and then we have to take the vector sum of magnetic moment of these individual domain. And the second hypothesis of Wies theory is that we have a domain, and within each domain this spontaneous magnetization is due to the existence of a molecular field. And this molecular field Hm is proportional to magnetization. That means Hm is proportional to m. Removing the proportionality sign, we will get proportional constant. This constant is denoted by lambda, and this lambda is termed as Wies field constant. And this Wies field constant, it is independent of temperature. So, when we have to find the effective field, this effective field will be the sum of external field and the molecular field Hm. That is, H effective is equal to H plus lambda m. So, these are the two basic hypotheses on which Wies theory of ferromagnetism is based. In my previous lecture, we have shown that on plotting a graph between m upon ms0 versus a, we have obtained a graphical solution for two equations which were m upon ms0 equal to kBT a upon n lambda g square mu b square g square, and the other equation was m upon ms0 equal to Ba. Here Ba is the Brillouin function, and in this expression Kb Boltzmann constant, T temperature, and the variable A is defined as A equal to G mu Bj upon Kbt. Lambda, as I have stated, is Wies field constant, G is Linde G factor, mu B Bohr magneton, and J is the quantum number, total angular quantum number. And this equation is temperature dependent, and this another equation is independent of temperature. So we have taken a plot and we have shown that magnetization arises only for the temperature range T less than Tc. We have taken three temperature range. The temperature range taken were T greater than Tc, T equal to Tc, and the third temperature range was T less than Tc. Here Tc is the critical temperature. And from the intersection method, we have shown that magnetization exists in a ferromagnetic material when T is less than Tc. This Tc is termed as Curie temperature. Now, in our today's lecture, we will discuss the variation of Tc and lambda. This is the plot between saturation magnetization and temperature. We can clearly see that when T approaches Tc, the saturation magnetization vanishes. This states that there is the existence of saturation magnetization only below the Curie temperature. Above the Curie temperature, transition takes place from one form of material to another form. That means below Tc, the material will be ferromagnetic, and above Tc, the material changes to a paramagnetic material. Now, we have discussed Brillouin function. This Brillouin function depends on A. I am writing the expression of Brillouin function. This is the expression of Brillouin function, and I am taking that A to be very much less than 1. That means we are considering near the origin. And for the small values of A, we can neglect this second term. So we are left with the term BA equal to J plus 1 upon 3J multiplied by A. That means if we plot BA with A, then we will get a line, straight line near the origin, and the slope of this curve will be equal to J plus 1 upon 3J. We have also derived the expression, this one, and this is equal to BA. So if we get a plot between BA and A, the slope of the curve from this expression will be equal to kBt divided by n lambda g square mu b square j square. So we are going to obtain the solution again by intersection method. And here it is evident that equating these two slopes, we will get this expression. J plus 1 upon 3J A is equated with this term. So using this expression and putting T equal to Tc, I get my value to be equal to 3 kb Tc upon lambda. This comes out to be ng square mu b square j plus 1. Here I am substituting mu to be equal to mu square to be equal to g square mu b square j plus 1. This term is the total magnetic moment per atom. From here we can see that Curie temperature Tc, this is directly proportional to lambda, as all these factors, these are constant. So this shows the dependence of Tc on lambda. Now I am going to discuss the temperature dependence of saturation magnetization. From this we will find that on which factor the magnetization comes from, whether it is coming from spin moment or orbital motion. Since we have derived our expression, this one, from here we are putting the values in our earlier expression, which was m upon ms0 kBta n lambda g square mu b square j square. I am putting the values I have obtained in my this expression. From these two expressions, I am getting the value of m upon ms0 to be j plus 1 upon 3j T upon Tc multiplied by A. Here M is the spontaneous magnetization and we are writing in the bracket T. This shows that magnetization depends on temperature and ms0 is the maximum value of saturation magnetization, which we can say that maximum value of spontaneous magnetization, and J is the total quantum number, T is a particular temperature and Tc is the Curie temperature. Now since m upon ms0 is plotted with T by Tc, from this equation we will get one curve, and from the another equation which we have derived earlier, this was the expression m upon ms is equal to Ba. We will get another expression for m upon ms. So we will obtain the solution by the method of intersection, and since here we have a one variable also, that is j, we'll put three values of j and we will obtain a curve. First of all, I am finding the curve for j equal to half. This is the curve for j equal to half obtained by this expression. Variable j equal to half, and on x-axis we have T by Tc and on y-axis we have m upon ms0. This is the shape of the curve, and the another curve, this is for j equal to 1, and the third curve, this is for j equal to infinity. Here I am showing the graph for all the three ferromagnetic materials, that is iron, cobalt and nickel. From here we can clearly show that the curve obtained for j equal to half coincides with the curve for the value which is obtained by using m upon ms equal to Ba. That means this expression. So from intersection method we can show that curve for j equal to half, this best fits our data. J equal to half shows that magnetization comes from spin rather than orbital motion. So the value of Linde factor will be G equal to 2, which is for spin motion, and it will not be equal to 1, which is for orbital motion. So we can say that ferromagnetism arises in the temperature range T less than Tc. This was our final conclusion which we derived in our last lecture. The so important conclusions are that in a ferromagnetic material, the magnetization exists for temperature T less than Tc. It is not possible when T equal to Tc or T is greater than Tc. The another important conclusion which we derived today is that spontaneous magnetization arises because of only spin motion. Orbital motion has no contribution to the magnetization. So these are the important conclusions which we derive in our today's lecture. Thank you students for watching.